In this video, I'm going to discuss particle physics, mainly focus on Edexcel curriculum. Right. Okay. So there are many subtopics in particle physics. I'll follow this order. First, I'll discuss about mass-energy relationship because according to mass-energy relationship, which was proposed by Albert Einstein in special theory of relativity, it's very important particle physics mainly when we consider about particle interactions. So not only particle interaction, even radioactivity, nuclear fission, nuclear fusion, in all those things, mass-energy relationship is very important. It violates the classical physics concept, that is conservation of mass or conservation of energy. Both are violated in this concept. Okay, so this is the first topic I'm going to discuss. After that, I'll explain about particle accelerators. So how to get high energy particles, so by using particle accelerators. So I'll briefly discuss about particle accelerators. There are 4 different types of particle accelerators we consider. Then I'll discuss about particle detectors, then about particle interactions, fundamental particles and particle interactions. Okay, when we think about mass energy relationship, this idea was, or this concept was proposed by Albert Einstein in special theory of relativity. It says that mass has equivalent energy and energy has equivalent mass. That means, in classical physics or in Newtonian mechanics, we say energy cannot be created or destroyed. We normally talk about conservation of energy. Same way we talk about in classical physics, we talk about conservation of mass. Mass cannot be created or destroyed. But here, according to this principle, we can convert energy into mass and vice versa. That is, we can convert mass into energy. So this idea was proposed purely by using mathematics in special theory of relativity. But later, there are experimental evidences to support this concept. For example, energy has equivalent mass. Energy has equivalent mass. The experimental observation we can say, when we accelerate particles in cyclotron, most of you would have learned that when we accelerate particles in cyclotron, what happens? One of the drawback of the cyclotron, we say that when the mass of the when the particles gain more and more energy, its mass increases. So how does the mass increase? Because of gain in energy. We supply energy by using electrical field, and they gain kinetic energy due to work done by the electric potential. So when the particles gain kinetic energy, what happens? Their mass increases. So it's a good example to support that energy has equivalent mass, or energy could be converted to mass. Also, there are evidence in particle physics. We are going to learn that, for example, when two particles collide, say for example, when two accelerated particles collide, we can create new particles. I'm using the word create. We can create new particles by using the energy carried by the initial particles. So these are the evidence to show that energy could be converted to mass. Same way, mass could be converted to energy. There are many evidences. For example, during radioactive decay. During radioactive decay, always the total mass of the products is lower than the mass of the parent nucleus. What happens there? The mass is destroyed. There will be mass deficit, and that equivalent energy of the mass deficit will be converted to kinetic energy of the particle released. Same way, nuclear fission, nuclear fusion also. What happens? The total mass of the products will be always lower than the total mass of the initial element. So there will be mass deficit, and the mass deficit has equal energy. That is the energy released during nuclear fission and fusion. Also during binding energy also, what happens during when we think about the binding energy also, the total mass of the nucleons. When you consider nucleus, there will be protons and neutrons. Protons and neutrons are nucleons. So the total mass of the nucleons, when you compare it with the mass of the nucleus, what happens? Mass of the nucleus is smaller than the total mass of the nucleons. So what happens? A certain amount of total mass of the nucleons is lost or converted to energy to bind the nucleons. That's called binding energy of the nucleus. So these are the good examples for mass has equivalent energy and energy has equivalent mass. Okay, so the mass and its equivalent energy are related by the equation E equal mc squared, or we can say when certain amount of mass is converted to energy, if I say a mass which is converted is delta m is converted to energy, then the equivalent energy which is created from this mass is given by delta E. Anyway, either way we can write mass has equivalent energy E, where C is the speed of light, or this is the amount of mass converted to energy. Delta M is the amount of mass converted to energy. That energy which is created is given by delta E equal delta M into C square. And we always, when we are using these equations, M must be in kilogram, C is 3 into 10 to the power 8 meter per second. So E will be given in joules. Okay, so by using this idea, we can create a new unit mass, because mass has equal energy. So if I write the M as a subject, M equal E over C squared. So this pattern is used as a unit of mass. Say for example, when we are writing the unit of, say for example, there are different types of units used for the same physical quantity. For example, unit of energy, we know joules. But for smaller energies, we don't write in joules, we write smaller energies in particle physics in terms of electron volt. Same way, smaller masses, mass of a particles such as protons, electrons, or even quarks, we can write their mass in terms of energy, which is written either electron volt or mega electron volt or giga electron volt or tera electron volt over C square. Is one of the accepted units. So for example, I can say mass of a particle X. So mass of a particle X, I can say 3 mega electron volt over C square. I can write this way, right? Because the 3 mega electron volt over C square means the equivalent energy of that particle is 3 mega electron volt. I can convert it to joules divided by C square. If I solve this, I will get the equivalent energy, equivalent mass in kilograms. Okay, this is a very important and very common question comes in particle physics. So remember that mass of a particle could be written in terms of unit, a new unit, which is given in terms of energy in electron volt or mega electron volt, giga electron volt, tera electron volt. One of it is divided by C square. This format we can use to represent the unit of a mass. So for example, the question could be like this. They can say unit of a particle, say unit of a mass of a proton. Mass of a proton is given in the data sheet equal 1.67 10 to the power minus 27 kilogram. They can ask to write this mass in terms of mega electron volt over C square. Find the mass of proton in mega electron volt over C square. It could be a question. How to solve this question or how to answer this question? Okay, so first I should find the equivalent energy of this mass in mega electron volt. So I can say E equal mc squared. So mass is given 1.67 10 to the power minus 27 into 3 into 10 to the power 8 all things squared. This is in terms of joules. To convert to mega electron volt, divided by 1.6 10 to the power minus 19. We know that 1.6 10 to the power minus 19 joules. 1 joules is equal to 1.6 10 minus 19 joules is equal to 1 electron volt. So to convert joules to electron volt, divide by 1.6 10 to the power minus 19. To convert to mega, 10 to the power 6 mega electron volt. Solve it, you will get the equivalent energy of the proton in mega electron volt. Okay, so that is equal to 939.4 mega electron volt. So I know that M is equal to E over C squared. So E is 939.4 mega electron volt over C squared. So that is the mass of a proton in this unit. Okay, so this is a very common question comes. First convert the normally they give the mass in kilograms, then convert it to equivalent amount of energy in terms of mega electron volt or giga electron volt or tera electron, depending on the question they ask. So here I asked to find the equivalent mass in terms of this mega electron volt over C squared. So that's the reason I found the equivalent energy of proton in mega electron volt. Then M equal E over C squared. So that will be the final answer. So mass of a proton is equal to 939.4 mega electron volt over C squared. Okay, this is another type of questions come. Mass of a particle X is 120 giga electron volt over C squared. Find this mass in kilograms. So this also a common question comes in the past paper, came in the past paper. So there I can say this is the particle mass is given. So I can say mass is equal to 120 giga electron volt over C squared. Solve this part. So 120 giga means 10 to the power 9. Electron volt means 1.6 10 to the power minus 19 joules divided by C squared 3 into 10 to the power 8 all things squared. So solve this, you will get the answer in kilogram. So final answer is 2.13 10 to the power minus 25 kilograms. So that is easy actually converting giga electron volt over C square. If it is a mega electron volt over C square, 120 into 10 to the power 6. Whatever the unit they are giving, convert to electron volt. Then to convert electron volt to joule, multiply by 1.6 10 to the minus 19 over C square, 3 into 10 to the power 8 all in square. Solve it, you will automatically get the answer in kilogram. Okay, next thing is about particle accelerators. Okay, why do we need particle accelerators in this topic? Actually, scientists want to find out what is the basic particle or what is the fundamental particle. Fundamental particle means that should not have any internal structure, right? That should be the basic type of particle. So if you want to see a basic type of particle, for example, we know all the matter made of atoms. Atoms consist of nucleus. We know that from the Rutherford alpha particle scattering experiment. We know that atomic structures, basically the nucleus consists of both protons and neutrons, and electrons are orbiting the nucleus. That is from the Bohr model. Electrons are orbiting the nucleus at different energy levels. And if you want to find out what is inside the electron, what is inside the nucleus, what is inside the protons, we need to break them into fragments, isn't it? So for example, if you want to break a proton into fragment, you need to hit the proton with a target with very high energy and break it into fragments. If you want to break something, say for example, if you want to break some object, you need to hit it with a target, is it, with a high energy. So the same idea, scientists got it. So they want to give high energy in the form of kinetic energy to a particle, and such as proton, and hit that proton with a target and break it into fragments to see what is inside the proton. So we should give energy means we should accelerate the proton. Neutrons cannot be accelerated because they are neutral particles. They will not feel any force due to electric field or magnetic field. So only the protons could be accelerated. So protons must be accelerated by using either electric field or magnetic field, and they should gain more energy. So only actually the electrons gain energy when they travel in electric field. When they travel in protons, when they travel in electric field, they gain energy. But when they travel in magnetic field, they'll try to move on a circular path. They'll accelerate, but gaining kinetic energy won't be there if the magnetic field is perpendicular. But if it is, if the proton travels in electric field, if we make a proper setup such that the protons experience electric field along the direction of motion, they'll gain kinetic energy. Then we can hit the proton with a target and we can break it into fragments. So to have such acceleration, to get acceleration, we need a machine. That machine is called particle accelerators. So actually particle accelerators are used to accelerate charged particles, mainly protons. Okay, so one of the purpose of accelerating a proton to high energy or high speed is to break it into fragments. There's another advantage of accelerating a proton, a charged particle such as proton to high energy. We can, now during collision what happens, the proton is carrying a very high amount of energy. During collision, suddenly the energy is lost. So that means the particle is decelerated suddenly during the collision. So the kinetic energy carried by the particle could be converted to equivalent amount of mass. That means we can create new particles during the collision. That's another purpose of particle accelerator. So the particle accelerators are used to create new particles by using the energy carried by the particle. The first reason. The second reason, the particle could be broken into fragments. For these two purposes, particle accelerators are used. Because you might ask how to create new particles. Yes, according to, I already told that mass has equivalent energy according to special theory of relativity. So their energy has equivalent mass also. So the energy carried by the particles could be used to create new particles during collision. So during collision, the particle will lose its kinetic energy because particle is being stopped suddenly during collision. So the kinetic energy carried by the particle could be used to create new particles. So the created new particles are also useful in terms of research. We are going to learn about how the new particles are created, different types of new particles created. We are going to learn that also. Okay, so here I am going to discuss about the particle accelerators. In your syllabus, mainly we consider two different types of particle accelerators. Linear accelerator, which is called LINAC, and cyclotron. All of them have, we should know their structure and their functions, and they have some drawbacks. How the drawback of the linear accelerator is solved in cyclotron. Then cyclotron also have drawbacks. How the drawback in cyclotron is solved by using synchrotron and synchrocyclotron also you must know, but we don't need to know the structure and function of the synchrotron and the synchrocyclotron. We should know only the structure and function of linear accelerator and the cyclotron. Okay, so this is the block diagram of linear accelerator. So it's a large vacuum tube. So inside a large vacuum tube, there are several drift tubes. Alternative drift tubes are connected to the same polarity of the AC signal. Difficult to draw, so I didn't draw. Say for example, I can say the odd number, the tubes, those are marked with odd numbers. So first one, third one, fifth one, they all will be connected to the same polarity of the AC signal. Then other drift tubes, the even numbers, second one, fourth one, sixth one, eighth one, and so on. They all will be connected to the same polarity of the high frequency AC signal. So actually all these drift tubes are kept inside a much larger vacuum inside a vacuum tube. So particle will be released from in front of the first drift tube. So what happens here? The high frequency AC signals provide electric field only in the gap between the drift tubes. So when a charged particle crosses the gap, it will experience a electrostatic force. So we can say electrostatic force means if it is a proton when you are accelerating it. So when the proton crosses the gap between the first drift tube and the second drift tube, what happens? The first drift tube will become positively charged and the second drift tube will become negatively charged. So the electric field will be from positive to negative. Proton is a positively charged particle, so the proton will be accelerated towards the second drift tube. So inside the second drift tube, it will move at constant velocity because inside the drift tubes, electric fields are shielded. That means inside the drift tubes, there are no electric fields. So the particle will move at the same velocity as it enters into the drift tube. But when it comes to the end of the second drift tube, what happens? The second drift tube, which was earlier negatively charged or negative polarity it had, now it will become positive, and the third drift tube will become negative. So the polarity will be switched every time when the particle reaches the end of the drift tube. So again the proton will be accelerated from second drift tube to third drift tube. Then it will move inside the third drift tube at constant velocity. Then when it reaches the end of the third drift tube, which was so far negative, but now it will become positively charged, this will become negatively charged, the fourth drift tube will become negatively charged, so it will be accelerated again. Like that, the particle will be accelerated again and again only when the particle crosses the gap between the drift tubes. Okay, so like that, there will be several drift tubes, more than 500 I think. Drift tubes will be there. The total length of the linear accelerator is almost 3.5 kilometers. So finally, the particle reach the target with large amount of kinetic energy. So here you must know that the common questions comes, they ask to describe. So you can say the length of the drift tubes increases along the direction of motion of the particle. You can say about that. I'll explain why should it increase. I'm telling about the structure. The length of the drift tubes increases along the direction of motion of the particle. Also, the gap between the drift tubes slightly increases along the direction of motion of the particle. Then you can tell about alternative drift tubes are connected to the same polarity of the high frequency AC power supply, and electric field is applied only in the gap between the drift tubes, and the electric field is shielded inside the drift tubes. There is no electric field inside the drift tube. You can say these are the structures. Function, you can say whenever charged particle crosses the gap between two drift tubes, it will gain kinetic energy. So we can say the equation for the gain in kinetic energy, we can write gain in kinetic energy. So gain in kinetic energy equal work done by the electric potential, W equal QV. So the charge of the particle, if I say Q into V, V is the potential difference applied across the drift tubes. So this is the energy gained by the charged particle during one acceleration, or whenever it crosses a gap, one gap, it gains this amount of kinetic energy. So if there are capital N number of gaps, so the total gain in kinetic energy, so total gain in kinetic energy equal to N number of gaps between the drift tubes into QV. This is the answer you can use whenever they give a numerical calculation. Number of gaps between the drift tubes into charge of the particle being accelerated times the potential difference applied across the drift tubes. How much of time, how long will it spend inside the drift tube? Actually, the time spent by the particle inside the drift tube is equal to half the period of AC signal. You know, we are using a AC signal to provide the voltage because it has to switch every half the period. So the time spent by a particle inside a drift tube is equal to half the period of the AC signal. So we can say approximately, because we don't have any proper time for time spent by the particle inside a gap. So but we can say approximately time spent by the particle inside the LINAC is equal to number of drift tubes into half the period of the AC signal, we can say. Okay, why should the length of the drift tubes increase along the direction of motion? You know, the AC signal has constant frequency, constant period. I already told you that the time spent by a particle inside the drift tube is the same, which is half the period. So that it spends same amount of time inside each drift tube, but the speed of the particle or the velocity of the particle is increasing along the direction of motion, but it should spend the same time means the length has to increase. You know that speed is equal to, it's inside the drift speed is moving at constant speed. So the distance traveled inside or the length of the drift tube should be how much? The speed of the particle at which it's entering into the drift tube into the time it spends inside the drift tube. The time it spends inside the drift tube is equal to half the period. So that is constant. The speed is increasing every time compared to the speed of the velocity of the particle inside fifth tube and sixth tube. When you compare, here the speed is more compared to here. So speed is more, it has to be the same time means the length has to increase. So that's the reason, to maintain the same time inside each drift tube, the length of the drift tube has to increase. The same way, why should the gap increases? There also the average velocity of the particle compared to here and here. Here the average velocity is more compared to here because the particle is accelerating. That's the reason I'm using the word average velocity. So the average velocity here is more than here. So it has to spend the same time inside here also compared to here. So the reason the gap between the drift tubes also should increase. Okay, so those are the questions normally comes. If there's a calculation, the calculation will be based on this one. Okay, what's the drawback of linear accelerator? The amount of energy gained by the particle is not sufficient to create massive new particles. I told by hitting a target, the energy carried by the particles such as proton could be converted to new particles, but the energy carried by the particle is not sufficient to create massive particles for the research purpose. So if you want to increase the energy of the particles here, the only thing is there are two possibilities. You have to increase the voltage applied across the drift tubes, but you can't increase the voltage beyond a particular value because creating such high voltage is not possible. One reason, even if you create, it can cause spark, so that has a limitation. Actually, the voltage that can be applied between the drift tubes has a limitation. So the other possibility, you need to add more and more drift tubes, but adding more and more drift tubes also a problem because already it's almost 3 kilometer length, but when you add more and more drift tubes, what happens? The collimation will be problem. So protons, you can't just send one proton, is it? How do we create protons? Actually, it's hydrogen ions, is it? Hydrogen ions are the protons. So you can't send one proton. So it's a group of protons go, several thousands of protons. So when they go, there will be electrostatic repulsive force. There's a chance they can diverge and they can hit the walls of the tube. So when the length increases, that possibility is more difficult to collimate the protons. So because of that, it has a limitation, and that is the drawback of linear accelerator because the energy cannot be increased beyond a certain value. Okay, so to overcome this problem, the solution, they designed cyclotron. Okay, so this is the block diagram of cyclotron. So cyclotron consists of two D-shaped hollow cylinders. There's a small gap between the two cylinders. Magnetic field is applied perpendicular to the plane of the D-shaped cylinders. High frequency AC source is used to create electric field only in the gap between the two D-shaped cylinders, but magnetic field is applied everywhere over the D-shaped cylinders. The particle source is kept at the center. Okay, so here when the particle source releases a charged particle, what happens? The charged particle will move in magnetic field, and we know that according to Fleming's left hand rule, when it moves in a magnetic field, it will start to move on a circular path. So when the particle moves on a circular path And say for example, if it is a proton, when the particle crosses from first drift tube, say if I say this drift tube, sorry, this D-shaped cylinder 1, this D-shaped cylinder 2, if the particle crosses from second D-shaped cylinder to first D-shaped cylinder, the polarity of the AC signal will become this, will make this cylinder, the second cylinder as positive and the first cylinder as negative if it is a proton. Then the proton will gain kinetic energy. But inside this D-shaped cylinder, it won't experience any electric field because it experiences electric field only in the gap between the drift tubes. So it will move at the constant speed, no gaining kinetic energy when it reaches this end. But due to the magnetic field, it will move on a semicircular path. When it comes to this end, this will become positive, the polarity will change, and this will become negative. Again, it will gain kinetic energy. Like that, every time when the particle crosses the gap, the polarity will be switched such that the particle gain kinetic energy. So we know that we learned it in a magnetic field. When a particle moves in magnetic field, the force experienced by the particle is given by F equal VQV sin theta. But here the particle is moving, the velocity, you know, the magnetic field is perpendicular to the board, but particle is moving on the plane of the board. That's the way the setup is there. So the angle between the velocity of the particle and the direction of the magnetic field will be 90 degrees. So it will become theta equal to 90 degrees. So it will become VQV, the force acting on the particle. So this force will be the centripetal force for the particle. So F equal VQV is equal to mv squared over r. So balance it. VQV equal mv squared over r. So r will be equal to mv over VQ. That is P over VQ. This equation is given on the data sheet. They can ask you to derive it even in magnetic field topic, right? So R equal P over VQ. So that will be the radius of the particle. So whenever the particle crosses the gap between the two D-shaped cylinders, I told that the particle will gain kinetic energy due to the work done by the electric field. So when the particle gains kinetic energy, V will increase. When V increases, R will increase. So after crossing the gap, the radius of orbit of the particle will become larger than the previous its radius. So that's the reason every time after crossing the gap, the radius increases due to increase in speed and the particle will move on an outward spiral path. That's the reason the path of the particle will be always outward spiral path. They can ask you to explain this. You can explain it by using these equations. Why the particle moves on an outward spiral path. Also, they can ask you to derive the equation for the time spent by a particle inside the magnetic field. So I told that the time is like this. The AC signal, the time spent by the time period of the AC signal must be equal to time period of circular motion of the particle. That means when the particle is at this point, for example, if the particle is crossing the gap, when the particle is here, if it is positive, this is negative, particle will gain kinetic energy. Then when the particle reaches this point, this should become positive, this should become negative. So the particle has completed half the cycle. From here, it has completed half circle. Now the particle is here. When the particle comes back here, again, this should become positive, this should become negative. That means when the particle completes one full circle, the polarity should change twice. That means both should have the same period. The period of circular motion of the particle and the period of the AC signal must be the same. So what should be the period of the AC signal? I can find the period of the circular motion for the particle. So I can see in this equation mv over bq is equal to r. We know that v equal r omega in terms of circular motion. V equal r omega. And omega equal 2 pi over t. So r into 2 pi over t. So substitute that here. M instead of v, I can say r into 2 pi over t over bq equal to r. I just substituted V equal R omega, omega equal 2 pi over T. So M is of V, R into 2 pi over T over BQ. So this R and this R will get cancelled. So make the T subject from here. If you make the T subject, T equal, bring the T down, T equal 2 pi M over BQ. So this is the time period of circular motion of a particle in magnetic field. But I already told that the time period of the circular motion of the particle must be same as the time period of the AC signal. Means the time period of the AC signal also should be the same. Or in terms of frequency, if you want to say, I can say the frequency of the AC signal must be F equal 1 over T. So that should be BQ over 2 pi M. Or they can ask, what's the time spent by a particle inside a D-shaped cylinder? Means this is the time to complete one full orbit, means it's spending the time, same amount of time inside both D-shaped cylinders. So the time spent by a particle inside one D-shaped cylinder is pi M over BQ. Okay, so these derivations they can ask. Okay, so what is the drawback of this cyclotron? Means here you can get reasonably large amount of kinetic energy, but the problem is, you know that when the energy increases, mass of the particle will increase. I already told that the energy has equivalent mass. So when the energy increases, when you supply more and more energy to the particle, the mass of the particle will increase. So what's the problem? When the mass of the particle increases, what's going to happen? That in this cyclotron, the period of the AC signal is kept constant. How it is kept constant? So it's kept like such that the period of the AC signal is same as period of the circular motions. That's the way the time period is maintained. So initially both time periods tally. But what happens when the mass of the particle increases? The time period of the circular motion of the particle will increase, because when the M increases, T will increase. So particle will take more time to complete one full circular motion. But the frequency of the AC signal or the time period of the AC signal will remain same as earlier. So now what's the problem? There won't be any synchronization. Both will not synchronize with each other. So if the time periods are not synchronizing with each other, what's the problem? The acceleration will be disturbed. Say for example, when the particle reaches this end, this polarity should become positive and this should become negative, but when the time periods are not tallying with each other, it could happen other way. This can become negative and this can become positive, which might decelerate the particle. So there won't be any proper acceleration finally when the mass increases. Okay, so that's a drawback of cyclotron, but this problem was solved by using some method. So to overcome this problem, they handled it in two different ways. One method, but they it's actually not physics, it's actually technology. In technology, what they made, the problem is due to the change in time period of the particle. So they designed a cyclotron with a variable period of AC signal. So the period of the AC signal always varies according to the variation of time period of circular motion of the particle. So by using sensors, they monitor the variation in time period of the particle, circular motion of particle, and according to that variation, they change the time period of the AC signal also. That technology is used in synchrocyclotron. So the particle accelerator which maintains or which keeps that technology is called synchrocyclotron. Another way also they use to handle this problem, that is in which when the T increases because of the increasing mass. So when the M increases, if we monitor the increasing M, and according to that, if we increase the B, the magnetic field strength, we can keep the T constant, is it? So there's another technology in which when the M increases, it was monitored properly, and according to the increase in M, B also increased to keep the time period of circular motion of the particle constant. That technology is used in synchrotron. So there are two solutions. One is synchrocyclotron, in which the period of AC signal is changed according to the increase in mass of the particle. The other one is synchrotron, in which the magnetic field strength is increased according to the change in mass of the particle, and the time period was kept constant. These are the two solutions for the drawback in cyclotron. Okay, so we learned about particle accelerators, and they accelerate the particles or they gain energy, and the accelerated particles can hit a target and broken into fragments. So when the particles are broken into fragments, we should be able to identify the particles those are thrown away, or we should be able to identify the particles those are newly created from the energy carried by the accelerated particles. So the instrument which is used to identify the type of particles is called particle detector. So there are different types of particle detectors. They are bubble chamber, cloud chamber, spark chamber and drift chamber. But in your syllabus, mostly we focus on bubble chamber. The structure you must be able to describe, structure and the function. In all these type of particle detectors, remember that, can detect only the charged particles, but they can detect the neutral particles. How? They don't produce any track. Okay, so I talk about track, but actually how a particle detector detects a charged particles. All these particle detectors consist of medium. For example, bubble chamber consists of liquid hydrogen. Same way the cloud chamber consists of like vapor air mixed with alcohol vapor. Same way the spark and drift chambers also consists of inert gases. Anyway, whatever it is, whenever a charged particle travels through the medium which is consists inside the particle detector, when a charged particle travels through the medium, they produce track on it by ionizing the medium. So only the charged particles can ionize the medium and create track. Okay, so for example, if you fire a bullet inside water, when the bullet travels, it produces a track inside, is it? Something like that. Here, when a charged particle travels through the medium of the particle detector, they produce a track, and by using the track we can identify the properties of the charged particles. Neutral particles never produce track in all these types of particle detectors. So we'll firstly think about bubble chamber. Bubble chamber block diagram is given like this. So this is the block diagram, simple block diagram of bubble chamber. So it consists of liquid hydrogen. You know, all the gases could be liquefied by compressing the gas and by reducing their temperature. So this consists of liquid hydrogen. When a charged particle enters into the liquid hydrogen, the pressure will be slightly reduced by pushing the piston down. So the charged particle will be able to ionize the liquid hydrogen and boil by transferring its energy. The charged particle, by transferring its energy, it will be able to boil the liquid hydrogen. It has very low boiling point. Boil the liquid hydrogen only along its path. Okay, so the charged particle, when it enters into the liquid hydrogen, the pressure will be slightly reduced, so the boiling point will change, and the charged particle can ionize the liquid hydrogen by transferring its energy and boil only the liquid hydrogen along its path. So only along its path tiny bubbles will be formed during boiling of the liquid hydrogen. Magnetic field is applied perpendicular to the path of the particle. So if the particle is entering from left to right, magnetic field is applied perpendicular. That I can say the magnetic field is applied perpendicular to the direction of motion of the particle. So what happens when the particle produces track? What happens? The charged particle, when it travels through the magnetic field, it will move on a curved track. Is it? When a particle moves in a magnetic field, it will move on a curved track. We already know that R equal mv over bq, or R equal p over bq. According to that equation, the particle will move on a curved track. So What happens when a charged particle moves through the liquid hydrogen? It will boil, so it will form tiny bubbles. Due to the magnetic field, the track will be a curved path. Normally what they use bright yellow color light and they illuminate the track, and sensitive cameras are used to take the photographs. So the cameras are used to take the tracks produced by the charged particles. By using those tracks, we will be able to identify or detect the properties of the particles. So what are the properties of the tracks used to identify the properties of particles are? First one is by using the thickness of the track. By using the thickness of the track, we can detect the magnitude of charge of the particle. Larger the thickness, the charge of the particle is more. So there are equations for that, not in your syllabus. By using the thickness of the thickness of the track, the magnitude of charge of the particle can be identified. By using the direction of curvature of the track, we can detect whether the incoming charged particle or the charged particle passing through the liquid hydrogen, is it a positively typed particle or negatively typed particle, we can identify. Say for example, if you get a track something like this, I know that magnetic field is applied into the board and I got a track in this way along this direction, means I can identify what type of particle, whether it's a positive or negative, created this track. The track is curving upward direction, so I know the force is acting along towards the center of the curved path. I know the magnetic field is into the board. I can use Fleming's left hand rule. Magnetic field is into the board. Force is upward direction. So the direction of current, you can see the second finger, direction of current is along the direction of motion. So it is a positively charged particle. But if you get a track something like this, which type of particle is it creating this track in this bubble chamber? So here the direction of the magnetic force should be towards the center of the curvature. So this is the direction of the force. I know the magnetic field is into the board. Use the Fleming's left hand rule. Magnetic field is into the board. Force is this direction. So I know the second finger, that's the direction of current, is pointing opposite to the direction of motion, is it? So when I use the Fleming's left hand rule, current is this direction. But the particle is moving towards this way, the arrow, green color arrow is this way. The direction of current is opposite, means this is negatively charged particle. You know the direction of current is always opposite according to the conventional sign of direction of current. You know that in unit 2. Direction of current is always opposite to the direction of motion of the negatively charged particle. So here this track will be formed by a negatively charged particle. Okay, so by using the direction of curvature, we can identify the type of charge carried by the particle. By using the thickness of the track, we can identify the magnitude of charge of the particle. By using the length of the track, inside the bubble chamber from the photograph, we can find the energy carried by the particle. And by using the radius of curvature, we can find the radius of curvature of the track. So for example, if you have a track something like this, you can find the radius of curvature by drawing two tangents. Draw two tangents and draw a line perpendicular to the tangent. Yeah. Here also draw a line perpendicular to the tangent. I can draw here. Where they meet, that will be the center. So measure the radius. By using the radius of curvature of the track, we can find the momentum of the particle, R equal mu over v cube. So we can measure the radius from the photograph, and by using a proper scale, we can find the radius. We know the magnetic field strength we are applying here, that we know that. So we know the radius of curvature, we know the magnetic field we apply. The charge of the particle we can find by using thickness of the track. We can find the mv momentum. But if we know the speed at which it's entering into the particle by using the particle accelerator, we can calculate at what speed will it enter into the bubble chamber. So if we know the speed, we can find the mass also. Okay, so we can find all the properties of the particles by using the track, right? But for neutral particles, you can't find them because neutral particles never ionize the liquid hydrogen. Not only liquid hydrogen, even in spark and drift chambers also, they won't ionize the gases in those particle detectors. So what happens? Neutral particles never produce any tracks. Actually, what happens when a charged particle moves inside a medium, they will move in an inward spiral path. When a charged particle moves in a medium, it will move in an inward spiral path because due to continuous collision with the medium of the particle detector, the charged particle will lose its kinetic energy, so its speed will decrease. So when the speed decreases, according to R equal mv over bq, the radius of orbit of the particle will continuously decrease. When the v decreases, r will decrease. So actually, when a charged particle moves inside a particle detector, it will move on an inward spiral path. So sometimes there could be a question without telling which direction the particle is moving. So here I told the particle is entering from left to right, but they can give a question like this. Track is created in a bubble chamber. They can give the track something like this. Something like this type of tracks, a track is created like this in bubble chamber, and magnetic field is applied into the board. Magnetic field is applied into the board. Identify the type of charge carried by the particle. Okay, so here they are not telling from which direction to which direction the particle is moving, but I know that particle is moving from right to left because the radius of curvature is decreasing. When a charged particle moves in bubble chamber or cloud or spark chamber, its radius of orbit will decrease due to continuous collision. I already explained it. So now I know that the particle is moving this direction. So I need to find out the direction of the current by using Fleming's left hand rule. So I can take just one point here. So if I take a point here, the radius of curvature is somewhere this way. It's curved, so the center should be somewhere here. The force will act towards the center of the path. I know the force. I know the direction of the magnetic field which is given into the board. So only thing I need to find the direction of the current. Use the Fleming's left hand rule. Magnetic field into the board. Force is this direction. So direction of current, that is second finger indicating along the direction of motion. I know the direction of motion. They did not mention in the question, but I know it's moving from right to left because radius of curvature is decreasing. So I know the direction of motion. According to Fleming's left hand rule, the direction of the current also the same. So it is a positively charged particle. We can identify like this if there is a question in the exam paper. Okay, so when you compare bubble chamber with spark and drift chambers, bubble chamber is not that much sensitive to identify very short time living particles. What do you mean by very short time living particles means? We are going to learn about it in this chapter, in this topic. For example, earlier I already told that we can create new particles by using energy carried by the accelerated particles. So when accelerated particles collide with the target, the energy could be converted to matter and new particles could be created. There are several baryons, we are going to learn about it later. They can be created by using energy carried by the particles, but their lifetime is very short, maybe millisecond, microsecond, like that. So very short time living particles won't be able to ionize the liquid hydrogen and produce track. The time is not enough for them to ionize and produce bubbles and attract. Then only they can be detected, but the time is not enough. Their lifetime is very short. So those type of very short time living particles cannot be detected by using bubble chamber, but spark and drift chambers can detect these short time living particles. Also, the drift chamber can produce tracks in 3 dimensions. Say there are 2 tracks might be crossing each other in 2-dimensional diagrams. So when 2 tracks looks like crossing each other, but actually there is a gap between them, is it? So like that, the 3-dimensional images can be produced on the computer screen by using drift chamber, but in bubble chamber you can't create 3-dimensional screen, 3-dimensional images of the tracks. So compared to all these type of particle detectors, drift chambers are the most advanced and latest type of particle detectors. Okay, so next topic is fundamental particles. Okay, so what is meant by fundamental particle? Fundamental particle means particle that has no internal structure, or the particle that cannot be split further is called fundamental particle. Proton is not a fundamental particle. Proton is made of quarks. It has internal structure. Same way neutron also has internal structure. So neutron also is not a fundamental particle. But electron is a fundamental particle. You can't split electron further into fragments. So electron is made of what? It's made of energy. There's no other explanation. So what is the electron is made of energy, right? So electron is a fundamental particle. So when we talk about fundamental particles, so it's actually a very long procedure. Like there are a lot of methods to identify the fundamental particles by using the properties of the tracks formed, but none of them are in your syllabus. But how to classify the fundamental particles? So fundamental particles are mainly classified into 2 groups. They are quarks and leptons. So what are the differences between quarks and leptons? Means there are 2 main differences between quarks and leptons. The first difference is quarks will be interacted by, or quarks can be interacted by strong nuclear force. Leptons cannot be interacted by strong nuclear force. So what is strong nuclear force? You know, there are 4 different types of forces. In physics you would have learned that in unit 1. What are the 4 different types of forces? They are electromagnetic force, gravitational force, strong nuclear force, and weak nuclear force. So you know gravitational force is the force between any 2 masses. You would have learned that in unit 5 under gravitational field. Force between any 2 masses is called gravitational force. What is electromagnetic force? Means force between any 2 charges is called electrostatic force. Same way force between 2 magnets, or force between a magnet and a magnetic material is called magnetic force. Generally these 2 forces are together called, according to Maxwell's equations. The reason is Maxwell's equation. These 2 type of forces are generally called electromagnetic force. So there are 4 different types of forces. I told they are gravitational force, electromagnetic force. If they ask to state an example of electromagnetic force, you can say force between 2 charges or force between 2 magnets. They are electromagnetic force. Those 2 are well known to you. The third type is strong nuclear force. What is strong nuclear force? Actually, strong nuclear force is the force that bind the nucleons together. You can imagine, you know, the nucleus consists of several protons and neutrons. Protons are like charges. They will repel each other due to electrostatic force, but they are bound together. Why? Due to the strong nuclear force. Strong nuclear force bind the nucleons together, and it acts in a very short range only. So strong nuclear force acts inside the nucleus among the nucleons. That force bind the nucleons together, the strong nuclear force. So what is weak nuclear force? Weak nuclear force exists only during certain interactions. For example, during radioactive decay, when beta particle is emitted, that is due to weak nuclear force. So you can ask me, do we need a force for interaction? Yes, we need forces for interactions. For example, in chemistry, you would have learned that different type of bonds, for example, ionic bond, van der Waals force, ionic bond, covalent bond, or some books they say covalent bond force, ionic bonding forces, like that. So many type of forces you would have learned, and all the chemical reactions are basically due to the electrostatic force between the ions. Yeah, that's the reason for the chemical reactions. Like that, nuclear reactions. So chemical reactions is due to electrostatic force between different electrons and between different ions. But when you think about nuclear reactions like fission, fusion, radioactive decay, they are due to either strong nuclear force or weak nuclear force. So the forces are mainly involved in particle or nuclear reactions or particle or nuclear interactions. Okay, so strong nuclear force means that exists only within the nucleus, among the nucleons, very short range. So quarks can feel, or quarks can be interacted by strong nuclear force, but leptons cannot be interacted by strong nuclear force. The second difference, so I can write like this, the fundamental particles can be classified into two groups. One is quark, the other one is leptons. So what are the first difference between quarks and leptons? Quarks can be interacted by strong nuclear force. Leptons cannot be interacted by strong nuclear force. The second difference, quarks are massive. All the quarks are in the order of giga electron volt over c squared. In that order, the mass of any quark is in the order of giga electron volt over c squared. But all the leptons are, the mass of any lepton is in the order of mega electron volt over c squared. That means quarks are massive, leptons are lighter. So these are the two differences among quarks and leptons. So fundamental particle means it cannot be splitted further, or it has no internal structure. It's called fundamental particle. So fundamental particle is made of what? It's made of energy. So fundamental particles are identified into two main groups. How did they identify all these? Not in your syllabus, but you must know the classification only. So quarks are the fundamental particles are classified into two different groups. They are quarks and leptons. Quarks and leptons have two main differences. Quarks can be interacted by a strong nuclear force. I told already what's the reason for forces, where they exist. I already told those things. Quarks can be interacted by strong nuclear force. Leptons cannot be interacted by strong nuclear force. The second difference is quarks, the mass is in the order of giga electron volt over c square. We already learned this unit. Same way the mass of leptons are mega electron volt over c square. Okay, so all these they identified by using the tracks and theoretical standard model, but we don't need any of them, not in your syllabus. But how many different types of quarks did they identify? There are 6 different types of quarks. They are up quark, down quark. The notation is U, down quark, D, strange quark, S, then charm quark, bottom quark, and top quark. These are the 6 different types of quarks. Same way, there are 6 different types of leptons they identified. What are they? Electron neutrino, muon neutrino, tau neutrino, these are the 6 different types of leptons they identified. Okay, when you think about this generation, you can see in any book they say the first 2 quarks are first generation, they are second generation, and these are third generation. So what do you mean by generation? Actually, which era, when were they identified? Actually, you can see the mass is increasing from up to top. From up quark to top quark, the mass is increasing. Actually, when you think about all these quarks, if you ask me, do they exist naturally? No. Actually, if you think about proton, I said proton is not a fundamental particle. So they identified proton, you know, it naturally exists. Proton consists of two up quarks and a down quark. When you think about proton, it consists of two up quarks and a down quark. Same way, neutron consists of two down quarks and an up quark. So when you think about any matter on Earth or any matter in space, they are made of atoms. Atoms consist of electrons, they are orbiting the nucleus. So electrons are outside the nucleus. Nucleus consists of protons and neutrons. That's all. Any matter is made of atoms. Atoms, nucleus consists of protons and neutrons. Protons are consists of two up quarks and a down quark. Neutron is consists of two down quark and an up quark. Electron is a lepton. I already wrote that. So where can we find all these quarks? Strange quark, charm quark, bottom quark, top quark. Where do they exist? Actually, they don't exist naturally. They are created during particle interactions or when an accelerated particle collide with a target. I told energy carried by the particle could be used to create new particles. So actually all these quarks, they identified in the chambers, in the particle detectors by using their properties. So all these quarks actually they don't exist naturally. They are created by using the energy carried by the particle. They don't exist naturally. But up quark and down quark exist in the form of protons and neutrons like this. Same way, electron, you know, actually exists in the atom. Electron neutrino is released during fusion reaction. And all the quarks, like all the leptons, like a muon tau, also created during particle interactions. So you can see that the first up quark and down quark, they are first generation. They were identified long ago, somewhere 1950s, I think. So the top quark is the most massive quark. So it was identified in 1995, just 20 years back, almost, yeah, 20 years. So actually, they were able to create or detect up quark and down quark long ago because they are lighter. Less amount of energy is sufficient to create up quark or down quark. Even strange quark, charm quarks, they were identified somewhere in 1973 and 1979 or somewhere like that, because their mass is slightly more than these masses, but they also created by using a certain amount of energy. But create a top quark is not easy because its mass is very high. That means large amount of energy is required. So large amount of energy required means a particle accelerator which can give large amount of energy. Advanced particle accelerator was required to create a top quark, because higher mass means higher energy is required to create a top quarks. That's the reason that is third generation particle. The same way, tau and tau neutrino also third generation. These two are third generation. These two are second generation. These two are first generation. So they can ask why the mass of the particle increases with increasing generation. The only thing you can say, to create those particles, they don't exist naturally. To create those particles, large amount of energy required. Large amount of energy required means, well, advanced particle accelerators required. So it took time to develop such advanced particle accelerators. That's the reason top quark becomes third generation particle. Okay, so what is antiparticle or antimatter? That also in your syllabus. Antiparticle or antimatter means a particle and antiparticle. Say for example, if I say X is a particle, its antiparticle, generally denoted by a bar on top of it. Antiparticle means both should have the same mass. Both should have the same mass, but they should have same magnitude of charge. Same magnitude of charge, but opposite sign of charge. Opposite sign of charge. They should have same mass, same magnitude of charge, but opposite sign of charge. Say, so then you normal students, they ask electron and proton, are they opposite particle. Can we say antiparticles among them? No, they are not antiparticles among them, because when you think about electron and proton, they are not antiparticles among them, because they have the same magnitude of charge. This is -1, this is +1. So they have same magnitude, 1, opposite sign, but their masses are different. So they are not actually not as antiparticles among them. Then students, they ask neutron, does it have antiparticle? Yes, neutron has antiparticle called antineutron. So what about the charge? Yes, both have neutral, both are neutral, but when you think about neutron, I told neutron is made of 2 down quarks and an up quark. All the quarks have antiquarks. Say up quark has an antiquark called anti-up. Down quark has antiquark called anti-down. Same way, charm has anti-charm, bottom has anti-bottom, top has anti-top. So all the quarks have antiquarks also. That means you can create antiquarks also. That means they have the same mass, same magnitude of charge, but opposite sign of charge. So when you think about neutron, it's made of 2 down quark and up quark. You don't need to remember their charges, but you know charge of a up quark, you can get it from any book. I don't want to go in detail about it. Charge of up quark is +2/3e. Down quark is -1/3e. So if you find the charge of neutron, ddu means +2/3 -1/3 -1/3, that is equal to 0. So that's the reason charge of neutron is equal to 0. But when you think about antineutron is made of antiquarks. So antineutron, denoted by N bar, is made of 2 anti-down quarks and an anti-up quark. What could be the charge of it? So I told down quark has -1/3, anti-down has +1/3, opposite type of charge, same magnitude, +1/3. This one also +1/3, anti-up -2/3, so that also equal to 0. So charge of antineutron is also 0, but neutron has antiquark. That means, neutron has antiparticle called antineutron. Students normally get confused because when we define antiparticle, we say same magnitude of charge, opposite sign, and same mass. Is it? That's the way we define. But neutron has no charge, but even though it has no charge, it has antiparticle called antineutron because of its internal structure. It has opposite type of charge. Also, additionally, when we think about fundamental particles, we need to consider that their spin also becomes opposite when you think about antiparticles. But in your syllabus, spin is not much included, or maybe we can say it's not included at all. So we don't need to talk about spin quantum number when we talk about antiparticles. So this table shows quarks and relevant antiquark. Up quark, down quark, strange, charm, bottom and top quark. So you can see the charges, they are fraction, not integer. But up quark is +2/3, anti-up is -2/3 in terms of electronic charge. So +2/3 means +2/3 times 1.6 10 to the power -19 coulomb. This is electronic charge. Okay, electronic charge. One electronic charge is 1.6 10 to the power -19 coulomb. So +2/3 electronic charge means 1.6 10 to the power -19 must be multiplied by 2/3. Okay. Anyway, so down quark is -1/3, anti-down is plus, opposite sign. Strange quark -1/3, anti-strange is +1/3. You can see the quark and anti-quark, the relationship, they have positive, means the anti-quark will have negative charge. Right. Okay, so this table shows the leptons and the relevant anti-leptons. So electron, this is positron, we don't call anti-electron, that is called positron, right? Electron neutrino, anti-electron neutrino, muon, anti-muon, muon neutrino, anti-muon neutrino. So you can see here for all the neutrinos, the charges are 0 and their mass also almost equal to 0. Their charges are 0, but they have anti-muon also. Electron neutrino has anti-electron neutrino, but it's a fundamental particle. So how will they differ? Their spin quantum number becomes opposite. We don't need that, but anyway, in terms of spin, they becomes opposite. type. So that's the reason electron neutrino has anti-electron neutrino also. Okay, so when we think about quarks, quarks can exist alone. Electron can exist alone, just an electron. Same way, muon can exist alone, tau can exist alone. Electron neutrino can exist alone. Just one electron neutrino can survive, can stay. But when you think about quarks, they never exist alone. You can't find just one quark. You can't get just one up quark. Always quarks exist in groups. So what type of groups do they form? Three quarks together, they can be together. So three quarks can join together and form a particle. So a particle which is made of three quarks is called baryon. Same way, a quark and an antiquark can merge together and form a particle. So I told that quarks never exist alone. They always exist in groups. So what are the types of group they form? They can form a group with three quarks. That particle, a particle which consists of three quarks, is called baryon. They can form a particle with a quark and an antiquark. A quark and an antiquark can form a particle that is called meson. Then 5 different types of quarks they found only in Japan once. So 5 different types of quarks can form together, that is called pentaquark. So the another type, 3 antiquarks can merge together and form antibaryon. Okay, so what are the different types of particles do they form? Quarks they form. They can form like 3 quarks together. If they form, that is called baryon. 3 antiquarks, if they form, that is called antibaryon. A quark and an antiquark, if they form, that is called meson. Just not all 5 quarks come together, but they found it, not much in your syllabus, but anyway, 5 quarks together if they form, it's called pentaquark. So these are the only possible type of particles. They can be formed by quarks. Quarks never exist alone. They are always in a group. These are the only possible groups they can form. So any group of particle which consists of quark, it could be a baryon or antibaryon or meson or pentaquark, generally called hadron. Any particle that consists of quark is called hadron. Okay, so again, a particle which consists of 3 quarks is called baryon, 3 antiquarks is called antibaryon. A quark and an antiquark is called meson. 5 quarks together, a particle consists of, which is called pentaquark. All these particles, those are made of different number of quarks, as I shown here. General name is hadron. Okay, so remember that. But leptons can exist alone. Just an electron can be there. Just a muon can be there. An electron neutron, just one electron neutron can be there. But just one u quark cannot survive. Just one down quark cannot survive. It must be in a group, always the quarks. Okay, so just now I told a particle which is made of 3 quarks is called baryons. So there are several baryons created by using the energy of the accelerated particle. So Examples for few baryons: proton, which consists of two up quarks and a down quark. Proton notation is P. Within the bracket, what we put is the confinement, that the particle which consists of, that is, two up quarks and a down quark. Neutron, N notation, it consists of two down quarks and an up quark. Now these two particles, protons and neutrons, naturally exist and they survive, so they are naturally exist. But all other baryons, where can we find? Actually, they don't exist naturally, and their lifetime is also very short. When they are created by using the energy of the accelerated particles, I told earlier also, one of these are, they can be created, but what happened when they are created in the form of baryons, they survive for a very short time and again they will become energy. So examples: lambda particle. The notation for lambda is slightly different compared to actual notation what we use in V equal F lambda. So this is, but here this part we don't write in this notation. So the lambda particle, which consists of U, D and S, up quark, down quark and a strange quark. Sigma particle, which consists of two up quarks and a strange quark. Xi particle, which consists of up quark and two strange quarks. Omega particle, which consists of three S quarks. So like that, there are many. You can check it in the internet. There are around 25-30, more than that I think. You can find out baryons. They are made of energy. They are created by using the accelerated particles. And also you can create anti-baryons for these particles also. Antiproton made of U bar U bar D bar. Anti-neutron made of D bar D bar U bar. Anti-lambda can be U bar D bar. Like that you can create the antiparticles also, but you know there's a rule called selection rule, but those are not in your syllabus. But even if I say they can be created, sometimes if they are violating the selection rules, then they cannot be created. But anyway, generally I can say there could be antiparticle, antibaryons for these baryons also can be created. Okay, so earlier I told that a particle made of a quark and an antiquark is called meson. So there are two well-known mesons. They are pion and cation. Pion, there are three different types of pions. Positive pion, which is denoted by pi plus, negative pion, pi minus, neutral pion, pi 0. So positive pion, negative pion, neutral pion, they all are made of a quark and an antiquark. See, with cation also there are three different types of cions: positive cation, negative pion and neutral pion. You can see they all are made of a quark and an antiquark. So positive pion, you don't need to remember these internal structures. Positive pion, which is made of U quark and anti-down quark. Same way, negative pion is made of anti-up quark and a down quark. Neutral pion is made of U quark and anti-U quark. Same way, positive cation is S bar, that is anti-S and up quark. K minus is SU bar, K0, that is neutral cation, is S bar D. You can see that positive pion and negative pion consist of opposite type of quarks. This is U quark, anti-down quark. It is anti-up and down quark. So you can see positive pion and negative pion are among them antiparticles. You can see that positive pion and negative pion, they are antiparticles among them. Same way, positive cation and negative cation also, you can see S bar U, SU bar, among them antiparticles. Okay, so particle interactions. So what are the examples of particle interactions we are going to learn? If possible, we'll do few calculations related to particle interaction. Calculations means we can find out the energy release, those things, right? Okay, so when we think about particle interactions, generally I can say you know, in chemistry you learn about chemical interaction or chemical reactions. So chemical reactions is due to electrostatic force. I already told that. That forms bond between electrons or electron and ions. They form the bond due to, yes, different type of bonds. But here also here actually when we consider particle interaction examples, it could be nuclear interaction, nuclear reactions, or interaction between individual particles, not electrons. Just even electrons can involve, but other particles also. So here, which forces involved? The forces involved in this type of interactions are either strong nuclear force or weak nuclear force. Simple example, I can say nuclear fission, nuclear fusion, radioactive decay, annihilation, pair production. They all are examples of particle interactions. Same way you would write in chemical reaction. Here also we can write reaction equations for particle interactions. We are going to learn that, and we are going to find out whether certain interactions are valid. Okay, so how do we conclude whether certain interactions are valid? You know, during these particle interactions, all these types of particle interaction, I already told that fission, fusion, radioactive decay, then annihilation, pair production, all these type of particle interactions, certain factors must be conserved. What are they? The first one that must be conserved is total mass energy. So in classical physics, we talk about conservation of mass or conservation of energy. But in particle interactions, neither conserve, they both together conserved. The reason I already told that energy could be used to create new matter, new particles. Same way mass could be used to create new energy. So mass alone will not be conserved, energy alone will not be conserved, they together conserve. So in these particle interactions, unit 5 you would have learned that in radioactive decay, we always consider total mass energy should be conserved. Second one, charge must be conserved, total charge. That means before interaction, after interaction, the total charge of the particles must be conserved. Third one, total momentum. So all these you know. The fourth one is a new thing, I'll explain that later. That is Baryon number. It is normally denoted by capital B. The fifth one also new to you, that is Lepton number. That is denoted by capital L. Sixth one, strangeness. Okay, so this strangeness has a slight different property or different behavior. All the first five must be conserved in all type of particle nuclear interactions. I told that all these particle and nuclear interaction happens due to either strong nuclear force or weak nuclear force. In chemistry, remember again, all the chemical reactions happens due to electrostatic force or electromagnetic force between the different ions. Same way here, particle interaction, nuclear interaction happens due to either strong nuclear force or weak nuclear force, right? For example, I can say during nuclear fusion, that happens due to strong nuclear force, because molecules are, sorry, the nuclei are bound together. During fusion, the molecules of hydrogen nuclei bound together, so the interaction is due to strong nuclear force. But when you think about radioactive decay, emission of beta particle is due to weak nuclear force. So whatever it is, during all strong nuclear force interactions, all six must be conserved during all strong nuclear force interactions. That is called strong interaction. If an interaction occurs due to strong nuclear force, for example, fusion reaction, that is called strong interaction. In strong interaction, all the six factors must be conserved. But if the interaction happens due to weak nuclear force, example beta decay, there the first five must be conserved. Sixth one, strangeness is not necessary to conserve. It can conserve or not conserve, we don't care. So strangeness is not necessary to be conserved during weak interaction. Okay, so one by one we'll consider uh, how to use them in our syllabus, how they are used in our syllabus. Right, first one is total mass energy. So total mass energy, how can we use, how it is used in our syllabus. So based on total mass energy, there can be calculations. So for example, the calculations based on an particle interaction called annihilation or pair production. So I will discuss annihilation and pair production, and there I will show how to use total mass energy to calculate the total energy released or the wavelength of the particle, wavelength of the radiation released. So I'll use this total mass energy concept there. Then I'll think about charge, not much is discussed. Then we'll think about these things after that. Okay, so annihilation. So there I am going to show in this particular type of particle interaction how to use the conservation of total mass energy. So annihilation. What is annihilation? They ask in the past papers. So annihilation means when a particle interacts with its own antiparticle, both will vanish from existence and they will produce equivalent amount of energy in the form of photon. That reaction is called annihilation. When a particle interacts with its own antiparticle, say proton should interact with antiproton, electron should interact with positron is the anti-electron, or neutron should interact with anti-neutron, then both will vanish and equivalent amount of energy will be produced. So here also for this annihilation interaction we can write a reaction equation, but you write in the chemistry the same way here we can write. Say for example, if I say particle X interacts with its antiparticle X bar, generally we write bar for an antiparticle. What happens? It will produce equal amount of energy in the form of photons. So photons is denoted by, like this is the notation for photons. How many photons created? I am saying just n number of photons are created. Okay, so in this reaction, the particle X might be in motion, so it will possess kinetic energy and it has equivalent amount of energy of mass. So for example, particle X has mass, that mass has equivalent energy. So this also might be in motion, so it possesses kinetic energy. Both together when they interact, initially they have kinetic energy, they have mass, but you can say photon has no mass. Mass of a photon is equal to 0. So what happens? The total mass energy is conserved. So all the initial mass energy is converted to photon. Photon is a form of electromagnetic energy. It is a form of energy. So here I can say, when we think about the conservation rule related to total mass energy, I can say, we can't add joule with kilogram, is it? So we need to find common unit. So what we do, we always consider total mass energy, we write in terms of energy. Total mass energy, we write in terms of energy. Say kinetic energy of X plus kinetic energy of X bar. If they are in motion, they will have kinetic energy. Then X has mass. So I should add the mass with energy, but we can't add. Mass is in kilogram, energy in joule. So what should I do? I should find the equivalent energy of that mass. So mx, mass of x into c squared, that gives equivalent energy of particle which has mass mx, its equivalent energy, plus mx bar c squared, that is the equivalent energy of mass of the x bar anti-x particle, that is equal to, so everything I converted to equal amount of total amount of mass energy into energy equal to n number of photons created into energy of a photon. We learned that in unit 2 equal hf, E equal hf or hc over lambda. We learned that in unit 2. So n times hf. So here if we know all the quantities, these all quantities and how many photons are created, we can find the frequency of the electromagnetic radiation released or created during this annihilation process. Okay, we'll do a question now. Okay, so you can see this question. A positron with kinetic energy 2.2 mega electron volt collides with an electron at rest. So the kinetic energy of the electron is zero, is it? It's at rest. And they annihilate each other. Two gamma photons were created. Write the reaction equation for this annihilation. Find the frequency of gamma radiation released. Okay, so the first part, write the reaction equation. So you know the notation for so first part I can write E minus E positive, the positron is interacting with electron. That creates two gamma photons. That's enough. That's the reaction equation. Second part, I need to find the frequency of the gamma radiation release. So here, total mass energy is conserved. So electron is at rest, so its kinetic energy is zero. Positron is in motion. So first I can write the kinetic energy of positron plus kinetic energy of electron. Anyway, I know that is zero, plus mass of electron, positron, me plus c squared. That's the equivalent energy of mass of the positron. Equivalent energy of mass of the electron is equal to 2 times energy of photon hf. Okay, mass of electron is given in the data sheet, 9.11 10 to the power minus 31 kilogram. Mass of positron they won't give, but we know that mass of positron is same as mass of electron because positron is the antiparticle of electron. They have the same mass. So that also 9.11 10 to the power minus 31 kilogram. C is the speed of light, 3 into 10 to the power 8 meter per second. And how to convert electron volt, mega electron volt to joule? You must know that multiply by 1.6 10 to the power minus 19 into 10 to the power 6 because it's mega electron volt. Okay, we'll do the calculation now. So kinetic energy of positron is 2.2 mega electron volt. So 2.2 convert to joule, 10 to the power 6, 1.6 10 to the power minus 19 joules. Kinetic energy of electron 0 because it was at rest. Kinetic energy of electron, okay, yeah, I wrote the both, right. Mass of positron into c squared, mass of electron into c squared. I already told that they have the same mass. So I don't need to write twice. I can put 2 into 9.11 10 to the power minus 31 because 9.11 10 to the power minus 31 is the mass of electron. That is same as mass of positron also. So I don't need to write twice to save time. So I can write 2 times because both have same mass. 9.11 10 to the power minus 31, that is given in the data sheet, into 3 into 10 to the power 8, all things squared. So that is c squared I took it common, is equal to 2 times Planck constant is given on the data sheet. You can see that 6.64 10 to the power minus 34, I think. 6.63 10 to the power minus 34 into F. Solve it, you will get the frequency of the gamma radiation emitted. Okay, so that is 3.89 10 to the power 20 hertz. So that's the frequency of the gamma radiation released during this annihilation process. Okay, another type of particle interaction is pair production. What is pair production means? A photon spontaneously means in its own without any external stimulation. So a photon spontaneously decays into a particle and its own antiparticle. For example, a gamma photon can spontaneously decays into electron and a positron. This interaction is called pair production. Here also we can write reaction equation. Say for example, a photon notation is this is the notation for photon, like a gamma notation. A photon decays into a particle and an antiparticle. So the particle and antiparticle can have kinetic energy, or maybe they are just released depending on the question. We can use total mass energy. Here also total mass energy must be conserved. So related to that, we can do a question. Say for example, if I write energy of a photon is HF is equal to mass of x c squared plus mass of x bar c squared plus kinetic energy of x plus kinetic energy of x bar. This is the mathematical format related to pair production. Now we'll do a question related to pair production. Okay, so this is the question. A gamma ray photon decays into an electron and a positron. Calculate the frequency of the gamma radiation. So here nothing is mentioned about the kinetic energy of the electron and positron. So we should say assume electron and the positron were just created. So their kinetic energy is zero, just created, right? So if I write the reaction equation for this pair production, a photon decays into an electron and a positron. Okay, so HF equal kinetic energy of electron, we know that is zero, nothing mentioned about it. Kinetic energy of positron, that also nothing mentioned about it. Mass of electron in terms energy, me c square plus me plus c square, equal energy of mass of the positron, equal energy of mass of the electron. They have same mass because they are antiparticles among them. So H we know that 6.63 10 to the power minus 34 into F is equal to kinetic energy of electron. I should take 0 because nothing is mentioned there. Kinetic energy of the positron also should be 0, nothing is mentioned there. So mass of the electron, mass of positron are the same, so I'll both together 2 times 9.11 10 to the power minus 31 into 3 into 10 to the power 8 all in squared. Solve it and find the frequency. You will get the frequency will be equal to 8.2 10 to the 2.47 10 to the power 20. 2.47 into 10 to the power 20 hertz. Okay, so these are the 6 factors that must be conserved during any particle or nuclear interaction, already explained. The first one, how to use in calculations, already we did it now for pair production and annihilation. The charge, not a big thing, I will use that in a separate calculation, how to use charge. Okay, so the application of conservation of charge, momentum, I'll do it when I discuss the past paper questions. We'll go to Baryon number now. Okay, so what is Baryon number? It's a number assigned for particles, mainly for quarks. How it is assigned? Baryon number of a quark is equal to plus 1 by 3. So when you consider Baryon number, for any type of quark, its Baryon number is plus 1 by 3. So particle Baryon number. So for a quark, any type of quark out of 6 quarks, any type of quark, the Baryon number is plus 1 by 3. That's the way it's assigned. For anti-quark, minus 1 by 3. It's nothing related to charge. Okay, don't get confused this Baryon number with the charge. It's a separate, completely separate number assigned, right? So for anti-quark, minus 1 by 3. For a lepton, 0. Anti-lepton, that is also 0. Remember that. So what could be the baryon number of a proton? So you must remember the internal structure of proton and neutron. Proton is made of two up quarks and a down quark. Neutron is made of two down quarks and up quark. So what's the baryon number of a proton? So for proton, so the baryon number, it consists of three quarks, U quark and D quark. Each of them has plus 1 by 3. So plus 1 by 3, plus 1 by 3, plus 1 by 3. So that is equal to plus 1. So baryon number of a proton is plus 1. Same way, baryon number of a neutron, how much? That is consists of two down quarks and an up quark. Each quark has plus 1 by 3. So there are three quarks. So that also plus 1 by 3, plus 1 by 3, plus 1 by 3. That is equal to plus 1. So baryon number of a baryon is equal to plus 1, because baryon means it consists of three quarks. Each quark has plus 1 by 3. So three quarks together plus 1. So baryon number of a baryon plus 1. Remember that. Okay. Same way, what could be the baryon number of a meson? I already explained, meson consists of a quark and an antiquark. So baryon number of a meson, for a meson, baryon number, that is equal to plus 1 by 3 minus 1 by 3 equal to 0. So baryon number of a meson, it could be a positive pion or negative pion or neutral pion or positive cation or negative cation or neutral cation, whatever it is, the baryon number of a meson is equal to 0. Okay, so baryon number of a nucleus, what could it be? You know, when you think about a nucleus, nucleus consists of both protons and neutrons. O level we learned that total number of protons and neutrons are called mass number. Proton number both together, total number of protons and neutrons are called mass number. Each proton has baryon number plus 1. Each neutron has baryon number plus 1. So the mass number and the total baryon number of the nucleus are the same. Remember that. Mass number of a nucleus and the total baryon number of the nucleons of the nucleus are the same. Remember that. Okay, so the lepton number, how it is assigned? Lepton number also a number assigned for particles. For leptons, how is it assigned? For any lepton, the lepton number plus 1. For any antilepton, lepton number is equal to minus 1. For any quark, lepton number equal to 0. Same way, for any quark, the lepton number, any antiquark, the lepton number will be equal to 0. So when you think about lepton number for particle, so any lepton, lepton number plus 1, antilepton minus 1, any quark 0, antiquark 0. Same way, hadron, I already told that a particle which is made of quarks, general name is hadron. For any hadron, it could be a baryon or antibaryon or meson. The lepton number will be equal to 0, because any quark, any antiquark, the lepton number 0. Only for leptons. Those, what are the leptons? Electron, electron neutrino, muon, muon neutrino, tau, tau neutrino. Each of them has plus 1. Any antilepton, positron, anti-electron neutrino, anti-muon, anti-muon neutrino, anti-tau, anti-tau neutrino. Each of them has minus 1. Remember this. This won't be given in the exam paper. You must remember. Right? Remember these things. Okay, how strangeness is assigned? Strangeness is assigned like this. Only for strange quark, it is -1. Anti-strange quark +1. For any other quark, 0. Any other anti-quark, 0. Any lepton, 0. Any anti-lepton, 0. So strangeness is assigned only for strange quark. So particle so that is for S quark, for strange quark, -1, anti-S quark, that is anti-strange quark, +1. For any other quark, 0. Any other anti-quark, 0. Any lepton, 0. Anti-lepton, 0. So it's assigned only for S quark, strange quark, -1, anti-strange quark, +1. Also, I already told that only during strong interaction, the strange quark must be conserved. Otherwise, it's not compulsory. It is not necessary for strange quark to conserve. Okay, so you can ask me how to identify whether an interaction is strong or weak. I'll give an example now. Okay, we'll do few questions how to use these factors to identify whether reaction is valid or invalid. There I'll explain how to identify reaction is strong or weak. Okay, so actually if a reaction is strong interaction, I'll tell that now. So if an interaction is strong, that means that is happening due to strong nuclear force, that is called strong interaction. So if an interaction is strong, then type of quarks must be conserved. Type of quarks must be conserved. What do you mean by type of quarks? Means the total number of U quark on the left side must be equal to total number of U quarks on the right side. Total number of D quark on the left side must be equal to total number of D quarks on the right side. Total number of S quark on the left side must be equal to total number of S quarks on the right side. That means type of quarks conserved means it's a strong interaction. Weak interaction means type of quarks will not be conserved. So when we do questions, we'll check whether the reaction is valid. Then if the reaction is valid, then we'll check whether it is a strong interaction or weak interaction. Okay, I already told that mass number and baryon number are the same. So a nucleus, O level we learn a nucleus X, A, Z we generally write. A stands for mass number, Z stands for atomic number. The same way we can represent A by a baryon number. So nucleus can be denoted by X baryon number. Z is the charge, baryon number, and Z is the charge. Charge means the charge of the protons. So this notation could be used for any particles. Any particles could be written in terms of baryon number and charge. For example, when we write neutron, we write N10. Neutron is denoted as N10. So 1 indicates the baryon number of the neutron, 0 indicates the charge, not the atomic number, that is the charge. This is the notation for neutron. Electron E minus as a notation for electron, but 0 minus 1. This 0 indicates the baryon number of electron is 0, minus 1 indicates the charge. Same way for proton P11, 1 stands for baryon number, 1 stands for charge. Neutrino, that is baryon number 0 because neutrino is a lepton and it's a neutral particle, so its charge also 0. Remember the notation. Okay, we will we'll check whether this reaction is valid in terms of these quantities. So normally when we check, we consider only these factors. That is, we consider for the charge, baryon number, lepton number, and strangeness. Momentum and mass energy we don't check when we check for the validity of a reaction. Total mass energy, I already told, we use it for calculations. The momentum we will use during like when we think about a track and a neutral particle is released. I'll do that as a question. Then you will understand more about it, the application of momentum. Right. Okay, so here when we think about the validity of this reaction, first we will check one by one. Where the charge is conserved. So this charge is plus 7. So 7. This is 6. This is again plus 1 or 1. This is 0. So 6 plus 1, 7. That is valid. So we put a tick. It's conserved. Then we'll check for baryon number. This is nitrogen. Nitrogen baryon number. Mass number and baryon number are the same. N is nitrogen. C is carbon. Beta plus, that is positron. Beta plus and positron are the same. This is electron neutrino. So this baryon number is 13. This baryon number also 13. This baryon number 0. This is 0. That also conserved. Then lepton number. So you know nitrogen is all on nuclear reactions. So nitrogen nucleus has no leptons because it consists of protons and neutrons. So its lepton number equal to 0 because it has no leptons. Leptons are electron, electron neutrino, muon, muon neutrino, tau, tau neutrino. None of them are inside the nucleus. So here also the same argument, lepton number 0. Beta, beta is a positron. Positron is anti-lepton. Anti-lepton means -1. This is electron neutrino. Electron neutrino is a lepton +1. So before interaction the lepton number 0. After interaction if you add, that also 0, conserved. Strangeness. You know nucleus consists of protons and neutrons. Protons are made of U quarks and D quarks, neutrons also D quarks and U quarks, yes, so they don't have any strange quark. So strangeness of up quark, down quark is 0. Same way the nucleus 0, nucleus has no strange quark. This is a anti-lepton, positron is an anti-lepton, no strange quark. This also no strange quark, so that is conserved. So according to these 4 factors, it is a valid reaction. Okay, is it a strong interaction or weak? So it's a valid reaction, we found it, it's a valid reaction. We can ask, is it a strong interaction or weak interaction? I told, if it is a strong interaction, what should happen? Total number of quarks or the type of quarks must be considered. So total number of U quarks on the left side must be same as total number of U quarks on the right side. Total number of D quarks should be same as total number of D quarks. We'll check for the type of quarks, are they conserved? We know that, I already told that beta decay is a beta positive or beta negative, whatever it is. Beta decay happens due to weak nuclear force. So it's a weak interaction. Type of quarks will not be conserved. We'll see whether it is right or wrong. Okay, we'll check for type of quarks here. Anyway, we know, I already told that beta decay is an example for weak interaction. Right, we'll see how to find the type of quarks. So nuclear, the nitrogen consists of 7 protons, 13 baryon number or 13 mass number means 6 neutrons and 7 protons, is it? So 7 protons means the nitrogen nucleus consists of 7 protons. Each proton consists of 2 up quark and a down quark. Also it consists of 6 neutrons. Each consists of 2 down quark and an up quark. Okay, we'll see what is the total number of up quarks in the nitrogen nucleus. Total number of up quarks. How much they are? So it consists of 7 protons. Is it? 7 protons. This is the atomic number or charge, 7 protons. Each proton consists of 2 up quarks, means 7 into 2, 14. Then Neutron consists of one up quark. There are 6 neutrons, so plus 6 up quarks. So that is going to be 20 up quarks. Total d quark, how much? So 7 protons, each of them consists of 7. Each of them consists of 1 d quark. So 7 into 1, that is 7, plus 6 into 2, 14. How much is it? 21. Okay, after interaction, this is a lepton, no quark. This is a anti-lepton, no quark. Only this has the quark. So this consists of carbon. When you think about it, it consists of 6 proton and how much? 7 neutron. So total number of d quark or total number of u quarks here, we'll see total number of u quarks after interaction. So it consists of 6 protons. Each proton consists of 2. So 12 plus 7 into 1. So 7, 19. Total d quark, how much? Total d quarks. So this consists of 6 because each proton consists of 1 d quark. So 6 plus 7 neutrons, 7 into 2, 14, 20. So you can see now total up quark is 20, here 19, not conserved. 21, 20, not conserved. So type of quarks not conserved means weak interaction. Already I told that beta decay is a weak interaction. Okay, so here it's a weak interaction. Okay, second question. A neutron decays into a lambda particle. Its internal structure is given, quark composition is given, UDS. So lambda is a baryon. How do I know it's a baryon? It's made of 3 quarks, U quark, D quark, X quark. And a neutral cation, DS bar, internal structure. You don't need to remember the internal structure of K cions or pions or anything. You should remember only the internal structure of protons and neutrons. Protons, UUD, neutrons, DDU. That's enough for you, right? So first question, is it a valid reaction? So they can ask, is it a valid reaction? If it is a valid reaction, is it a strong interaction or weak interaction? Strong interaction means type of quarks must be conserved. Weak interaction means type of quarks will not be conserved. So first we should check whether it's a valid or invalid reaction. Okay, we'll check for that. Again, we'll start from charge. So this is charge. Neutron, the charge is 0. Lambda particle, charge is 0. Neutral cation, 0. So all 0, 0, it is conserved. So we can put a tick. Next one is baryon number, B. Neutron is a baryon. It's made of 3 quarks. So I already told that. Baryon number of a baryon is +1. So +1. Lambda is also a baryon. 3 quarks. So +1. It's a meson. Baryon number of meson is 0. I told that. Quark and antiquark. So 0. So before interaction, baryon number +1. After interaction, total baryon number +1 conserved. Then lepton. Neutron is a hadron. Hadron means made of quarks, is it? So it has no lepton. So lepton number will be equal to 0. Lambda is also a hadron made of 3 quarks. So lepton number 0. Same way meson is also hadron. Lepton number equals 0. So that also conserved. Strangeness. Neutron, you must remember the internal structure or its quark composition, DDU. So these are given, that will be given. This you must know, DDU. So it has no S quark. So strangeness of neutron is 0 because strangeness is assigned only for S quarks as -1, anti-S quarks +1. All the quarks 0. So neutron has no S quark, so strangeness 0. This has 1 S quark, so -1. This has 1 S anti-S +1. So before interaction 0, after interaction -1 plus 1 0, so that also conserved. So all conserved, so valid reaction. Is it a strong or weak interaction? Strangeness conserved does not mean it's strong interaction, because strangeness can be conserved for weak interaction also. I told that, remember, for strong interaction, strangeness must be conserved. For weak interaction, we don't care about it. Whether it's conserved or not, we don't care about it. So strangeness conserved does not mean it's a strong interaction, but strong interaction means strangeness must be conserved, right? Here strangeness is conserved, but it's a valid reaction. Okay, we'll check whether this is a strong or weak interaction, because it's a valid reaction. We know that it's a valid reaction. We are going to check whether it is a strong or weak interaction. So quark compositions are given. For neutron, you must remember. Okay, we'll check one by one. How many U quarks are there? Before interaction, there are 1 U quark. So number of U quarks, U quarks 1. Number of D quarks 2. Number of S quark, because there is S on the right side, so I'll write number of 0. There is no S quark before interaction. We'll check for after interaction. Number of U. How many? Here 1. There is nothing, so 1. Number of D. How many? 1, 2. So 2. Number of S. Okay, wait. Number of S quark. Here S quark, here S bar quark. So students, they think S quark, okay, how to count with S bar? We imagine whenever there is S and S bar, U and U bar, its anti-quark exists, we imagine they get cancelled. So here S quark, there is anti-S quark, so we should imagine 1 minus 1. So plus 1 minus 1, 0. Okay, whenever there is a quark and anti-quark, we don't count everything together. Number of quarks minus number of same type of anti-quark, right? So S quark 1, anti-S quark minus 1. It's not a strangeness. When we count like that. Quark and anti-quark. So the number of S quark 0. Now you can check here. U quark 1, U quark 1. You can see that 1, 1. D quark 2, D quark 2. S quark 0, S quark 0. Already we showed it's a valid reaction. So this is, since the type of quarks conserved, it's a strong interaction. Okay, third example. We'll check whether this reaction is valid based on these factors. Okay, charge K minus, is minus means minus 1. Proton, we know it's a positive charge, plus 1. Omega minus means minus 1. K plus means plus 1. K0 means 0. We'll see. Before interaction, minus 1 plus 1, 0. When you add total charge. After interaction, minus 1 plus 1, 0. So this is conserved. Then baryon number. K minus is a meson because it conserves charge and, quark and antiquark. So meson means baryon number 0. We know proton is a baryon plus 1. Omega consists of 3 s quarks, so it's a baryon plus 1. K plus is a meson because it consists of quark and antiquark, 0. Baryon number for a meson. Then this also meson 0. So before interaction, baryon number plus 1. After interaction also, baryon number totally plus 1. So that is conserved. Then lepton number. It has no leptons because it's a hadron made of quarks. So lepton number 0. Proton is a hadron, lepton number 0. Omega is a baryon, it's a hadron. So all are hadrons. So lepton number 0 conserved. Strangeness. K minus has 1 s quark, so minus 1. S quark minus 1, strangeness. Anti-S quark, strangeness plus 1. proton has no strange quark. You must know its internal structure, UUD. You must remember that. It has no strange quark, so strangeness is 0. This is each of them minus 1, so minus 3. This is plus 1. This is plus 1. We will check whether it's valid. So strangeness, when we consider, here before interaction minus 1, this is 0, so totally minus 1. After interaction minus 3, plus 1, plus 1. So plus 1, plus 1, plus 2, minus 3, minus 1. So total strangeness after interaction minus 1. Before interaction also minus 1. So conserved. So it is a valid reaction. So valid reaction, strangeness conserved does not mean strong interaction. I already explained. So we'll check whether it's a strong or weak interaction by using type of quarks conservation. Okay, we'll check whether the reaction is strong or weak. Okay, so we'll check one by one the type of quarks. So before interaction, total U quark. How many U quarks are there? Here 1 plus 1, 2. Here anti-U quarks. So 2, 1 plus 1, 2. Minus 1. I told if there is a quark and same type of antiquark, you should subtract the antiquark from the quark numbers. So 1 plus 1, 2, minus 1, that is equal to 1. Number of U, total number of U, 1. D quarks, how many D quarks are there? Just 1. Total S. How many S quark? 1. Okay, so total U1, total D1, total S1 before interaction. After interaction, total U, how many are there? Here 1, only 1, right. Total D, how many are there? Just 1, yes. Total S. Here 3, here minus 1, minus 1, so 1. Okay, now we'll check what's happening. Number of U, 1. Number of U, 1. Conserved. Number of D, 1. Number of D, 1. Number of S, 1. Number of S, 1. So, type of quarks conserved. So, strong interaction. Okay, so far we learned all factors, the conservation properties, and how to use. I did a calculation based on mass energy calculation. I already did it. If you want, I can do more. We'll see. Then baryon number, lepton number, strangeness, charge, how to use, we already learned. Only thing remaining is momentum. How can we use momentum? Okay, so there was a past paper question, not exactly the same, but something like this. A question appeared. They gave a photograph of a track, something like this. So how to use the property, the conservation of momentum, to determine whether a neutral particle is created or neutral particle is created during a decay of a charged particle. You know that already we learned that neutral particles won't produce track in any type of particle detector. So we can identify whether there's a decay which produce a neutral particle by using conservation of momentum. So the question is something like this. They gave the track, it's a photograph. I drew it on the board. A positive particle. So this track is due to positive particle. You know there's a magnetic field applied. So there is a track, and the track won't be a straight line. If there's a magnetic field, you know that the track will be a curved path. So positive particle decays at point Y. So at this point it's decaying. Explain the evidence from the photograph for the production of neutral particle at y. So you know that at this point y, a positive particle is moving, and at this point y it's decaying, but when it decays, it creating another positive particle. How do I know the part which creates also positive? Because the direction of spiral is the same. Say it's spiraling this way, here also spiraling this way. So it's not a negative particle. If it's a negative particle, the spiral would have gone other way, opposite direction, is it? In the magnetic field. So same positive particle is created, but there is a neutral particle also. What's the evidence? How can I find it? Conservation of momentum. So think about conservation of momentum, vector diagram for momentum at point y. If I think about a tangent, you know, when a particle moves on a curved path, we learned that in unit 1 projectile motion, always the velocity will be along the tangent. So velocity is along the tangent means momentum will be along the tangent. So if I think about just at point y, before decay, say I can say the positive particle, let it be, say that let it be x, positive particle. So the particle x which is creating this track is decaying at that point. So its momentum just before decay will be along the tangent, should be this way. If I draw a tangent here, it should be this way. After decay, there is another positive particle, let it be capital Y. So that is moving this way. So that is this way. This is x. So what's the conservation law says? Conservation of momentum says during decay, the total momentum must be conserved. That means momentum of x in terms of vectors, if I write momentum of x must be equal to, P stands for momentum of x particle at the point y must be equal to momentum of y, but there must be something else, because you know they have different directions. There should be a particle which cannot produce a track, maybe a neutral particle, momentum of a neutral particle, let it be say n, neutral particle, capital N, not a nitrogen. So I'll put neutral particle z, z0. Understand? So by using the vector diagram, I can draw the resultant vector of these two must be equal to this momentum. So the momentum of x bar could be like this. If I draw a parallel line for the momentum, this is the momentum of x plus, this is the momentum of y. So the resultant of these two must be equal to momentum of the x bar. So that means momentum of y should be something like this. This is the momentum of y. So z, if I know the momentum of these two values, I can say the momentum of z, where it would have gone, the neutral particle, which direction it went, also I can find from the vector diagram. So the addition of the momentum of these two must be equal to this one. I know the momentum of x, I know the momentum of y, I can get it from the tracks. So momentum of z must be something like this. So I can find out the z would have gone something this way. Okay, so like this, no calculations, but we can have a explanation type of questions based on conservation of momentum. Okay, so before answering this question, I should say something about colliding beam colliders and fixed target colliders. I already explained that when I discussed May-June 2022 paper. May-June 2022 paper. Unit 4. Question number 13. Question number 13B. Page number 11. Okay, I already explained. The same question appeared in that paper. The question was In some experiments, high energy electron collides with stationary atom. In another experiments, beam of high energy electrons traveling in opposite directions collide head on. Those are called colliding beam colliders. Those are moving in opposite direction and collide. Other one is called fixed target colliders. Accelerated particle move and hit a fixed target. New particles can be created from collisions where the colliding beam colliders deduce which type of collision is more likely to produce new particles. We know colliding beam colliders will produce massive new particles. The reason, again I'll explain, but I already explained in this past paper discussion, already it's uploaded in my channel, you can go through it. Anyways, you know that when two identical oppositely traveling particles, when they travel at the same kinetic energy, the initial total momentum will be equal to 0. You know total momentum is conserved. We already explained just now. So total momentum conserved means when they travel in opposite direction before collision, so the initial total momentum will be equal to 0. It should be conserved. So the final total momentum also must be equal to 0. So final total momentum equal to 0 means when you add all the momenta of the products, it must be equal to 0. But that does not mean all the particles are at rest. But there will be a chance, 1 in maybe, I don't know, 1 million or something like that. There's a chance all the created particles will be at rest. If that happens, what will be the advantage? If all the particles created are at rest, the kinetic energy after collision will be equal to 0. So all the initial total energy will be used to create new massive particles. Okay, so that's the advantage of colliding beam colliders compared to fixed target colliders. Okay, so in this question also it's happening in a colliding beam collider. So that means two protons are traveling in opposite direction. I did not write that, but that's the question. Two protons are traveling in opposite direction at the same kinetic energy, and when they collide, these particles are created. A proton, 7 positive pions, 7 negative pions, positive cation and the lambda particles are created, and the mass of each of these particles are given. The question is, calculate the minimum kinetic energy. So the word minimum kinetic energy of each proton. So of each these protons, those are traveling in opposite direction, in mega electron fold for this interaction. That means minimum kinetic energy, if you want to create, means the only possibility, all the created particles won't have kinetic energy. All the created particles are at rest. So these particles are created, but they all are at rest means I put the right side minimum energy. So left side also will become minimum energy. Then now I can use the total mass energy conservation. So total kinetic energy of all these particles are equal to 0. So they all are at rest. They are just created because I want to find the minimum kinetic energy. Okay. Proton, they are moving in opposite direction. So they have the same amount of kinetic energy. So I can say kinetic energy of proton plus kinetic energy of proton plus mass of proton c squared plus mass of proton c squared. Total mass energy I am calculating is equal to, all of them has kinetic energy 0, but here mass of proton c squared 7 times mass of pi plus c squared 7 times mass of pi minus c squared. They are just created, so they are equivalent energy of the mass, plus mass of k plus c squared plus mass of lambda c squared. None of them has kinetic energy because they are just created. We are finding the minimum energy of these protons. Okay, so mass of proton c squared, mass of proton c squared will get cancelled. Now algebra. So according to algebra, these two will get cancelled. Okay, so kinetic energy of proton, 2 times kinetic energy of proton. They are, you know, in colliding beam colliders, they travel in opposite direction with the same kinetic energy. So 2 times kinetic energy of proton plus mass of proton c squared. Mass of proton is given in mega electron volt, 938 mega electron volt over c squared into c squared. Good. These two are going to get cancelled. Is equal to, this got cancelled 7 times mass of pi plus, mass of pi minus. You know they are antiparticles. They are positive pion, negative pion, they are antiparticle. They will have same mass. That's correct, because here they are same mass of pi plus, mass of pi minus. So I can say 7, 7, 14. So I don't need to do separately. 14 times 140 mega electron volt over c squared into c squared. Is it 7 plus 7, 14? They have same mass, pi plus and pi minus. So 14 into 140 mega electron volt c squared into c squared plus mass of k plus. Mass of k plus is 494 mega electron volt over c squared into c squared plus mass of lambda, that is 1115. So what I am finding is the kinetic energy of protons, which is minimum. Solve it, you will get the final answer. So easy, c squared, c squared, c squared, c squared, all will get cancelled. Solve it and find the kinetic energy of proton, which is minimum. Solve it. Okay, so the answer 1315.5 mega electron volt. C squared will get cancelled, so mega electron volt. So that's the answer. They asked to find it in mega electron volt. Okay, so that's the minimum kinetic energy of the proton. So how do I decide the minimum kinetic energy? All the particles, those are created as zero kinetic energy, no kinetic energy. That can happen during colliding beam colliders, when the protons or particles carry same magnitude of kinetic energy and travel in opposite direction, because momentum is conserved. So you can see the May 2022 past paper. They are explained the difference between colliding beam colliders and fixed target colliders. Okay, so I have discussed for 2.5 hours all the topics in particle physics. I discussed, I did not miss anything, and I showed few examples related to past paper questions. I did not discuss this Rutherford alpha particle scattering experiment. It's not a big issue. You can learn from any textbook. And if you think you want more questions to discuss related to particle physics based on past papers, put it in the comments. Depending on my free time, I can discuss before the May-June exam. I hope you understood and enjoyed it. Bye.